Torque measures the force that causes an object to rotate about an axis. So just as force is what causes an object to accelerate in linear kinematics, torque is what causes an object to acquire angular acceleration. There are two types of torque, which are static torque and dynamic torque. So when the object does not experience angular acceleration when supplied with torque, the torque applied is the static torque. Meanwhile, a dynamic torque will cause the object to experience angular acceleration. As torque is applied to the rod, it will twist and the rod will rotate to a new position. So the angle between the original and new position is referred to as the angle of twist. So the amount of shear strain is determined by the angle of twist, the distance along the radius of the shaft, and the length of the shaft. So to determine the strength of the circular shaft in withstanding the torsion, torsion testing can be performed to obtain information such as torsional shear stress, maximum torque, shear modulus, and breaking angle of a material or the interface between the two materials. The objective of the experiment is to investigate the relationship between torque and the angle of twist of a circular cross-section bar and to determine the modulus of rigidity of the materials. So to achieve the objective, a base frame that has a clamp at one end and a ball bearing in the housing at the other end will be used. A short shaft in the bearing has a 3-jaw chuck facing the clamp and a torsion head at the outer side. A hang cord is wound around the torsion. The circular rod will be gripped in place by the clamp and the rotating chuck. To record the twist angle, an arc-shaped scale of degrees is mounted on a base that can be moved along the length of the rod. So the rod will be attached with a pointer to indicate the angle of rotation of the rod when the loads are applied to the hanger cord. So the scope of this experiment is to compare the torsional behavior of 4 different solid bars made of steel, aluminum, nylon, and copper alloy. So incremental torsional loading will be applied from 5 Newton to 40 Newton to each material specimen. The twist will be measured at only from 200 mm and 400 mm from the fixed clamp. So to the theory, a torque is a moment that twists a structure. Unlike axial loads which produce a uniform or average stress over a cross-section of the object, a torque creates a distribution of stress over cross-sections. So if we have a rod or shaft, when the torque is applied to the structure, it will twist along the long axis of the rod, and its cross-sections remain circular as depicted in the illustration of weaker one, when a circular shaft is subjected to a torsional load. Within a certain range of torque values, the twist angle is proportional to the torque. It also shows that the angle of twist is proportional to the length of the shaft. So when a circular shaft is subjected to the torsion, every cross-section remains plane and undistorted. These are the characteristics of both solid and hollow circular shaft, except for non-circular cross-section shafts such as rectangular bars. So the equation below can be obtained to conclude that the shearing strain in a circular shaft varies linearly with the distance from the axis of the shaft. So when we arrange the equation, we can find out that the shearing stress in radian is equal to the length from the center to any point in the circle of the shaft times the angle of twist in radian over length of the shaft. The shearing strain will be maximum on the surface of the shaft if the length of any point in the circle is equal to the radius of the shaft. As the torque is such that all shearing stress in the shaft remain below the yield strength, Hooke's law will be applied and there will be no permanent deformation. So shearing stress is equal to the shear modulus of the material times the shearing strain. So combining Hooke's law with equation 3, we will get the equation below that shows that the shearing stress varies linearly with the radial position in the section. So the shearing stress is equal to the length from the center in any point of the circle over the radius of the circle times the shearing stress, maximum shearing stress. The polar moment of inertia describes the cylindrical object's resistance to torsional deformation when the torque is applied in the plane that is parallel to the cross-section area that is perpendicular to the object's central axis. So for a solid circular cross-section shaft, the value of Ga can be calculated from the formula below. So the solution for the angle of twist can be solved using the Hooke's law by substituting equation 2 and the equation maximum shearing stress into the Hooke's law. So the equation below can be obtained. Experimental setup. As depicted in figure 2, for the machine and setup, the apparatus we use are solid bar, which we use 3, steel, aluminum, and nylon bar, and then the torsion bar testing machine with a load, ruler, and digital caliper.
Methodology. First, the apparatus will be set up as in the figure 3. Second, the steel solid bar will be clamped in the position and the light hanger will be placed on the cord. Third, the rotation scale will be adjusted to the 200 mm from the fixed clamp and the pointer will be set to the 0 degrees. Fourth, the load of 5 Newton will be incrementally added until reaching maximum load and the twist of the specimen for each equipment will be recorded in table 1. After removing the rod, the rotation scale and the pointer will be repositioned to the 400 mm from the clamp and step 4 will be repeated. the specimen will be replaced with the aluminium solid rod, copper alloy solid bar, and the same procedure will be repeated again. And the diameter of the whole rod is to be measured, and the torque as the respective twist will be calculated and will be recorded in table 2 and 3.
Next is the result. The table 1 below shows that the data for steel solid bar. The diameter of the solid bar is 6.29 mm. As you can see, there is an increment of 5 Newton from 5 Newton until 40 Newton of the wave of load. In this experiment, we will record the angle of twist of load in degree, and at the same time we will change it to radian. So to calculate the torque, we will use the T equals to R times F to calculate it. For example, the radius of the solid bar is 3.145 times 5 Newton to get the torque. We will repeat the same step until the 40 Newton. The table 2 below shows that the data for aluminium solid bar, the diameter of the solid bar is 5.12 mm. As you can see, the wave of load is same as the previous one, but the difference is for this solid bar, when the wave of load is 25 Newton, at the 200 mm twist is overload, so we can't record anything after the 25 Newton load. So next is the nylon solid bar. The diameter of the solid bar is 6.08 mm, and the increment of the wave of load is different from the previous one, which is the increment of the wave of load is 1 Newton from 1 Newton until 8 Newton. As you can see, when the wave of load is until 8 Newton, at the 200 mm twist is overload. Next is discussion part. We will draw the graph of angle of twist against torque for both of the 200 mm and 400 mm of the 3 material solid bar, and we will calculate the linear equation for each graph.
The first question is, to what extent does the experiment verify the torque or twist formula based on the graph plotted? The formula of angle of twist is shown below. Angle of twist equals to torque times length divided by polar moment of inertia and modulus of rigidity. According to the y equals to mx plus c, as you can see, the gradient of the graph is equals to length divided by polar moment of inertia and modulus of rigidity. To get the modulus of rigidity, which is g, we will rearrange it from this equation. We take the steel solid bar as an example. The diameter of the solid bar is 6.29 mm. For the length of shaft over 200 mm, we know that y equals to 0.00196x plus 0.00563. The gradient of the graph is 0.00196. After that, we will calculate the polar moment of inertia J, which is the formula is J equals to pi times d over 2 power of 4 divided by 2. We will get the value of J, which is 153.67 mm power of 4. Next is modulus of rigidity, G. G equals to L over J times M. After we sub the value inside, we get the value of G, which is 735.31. For the length of shaft over 400 mm, the y equals to 0.00123x minus 0.028. The m is equal to 0.00123. The polar moment of inertia J is remain, but due to the change of the value of gradient, so the modulus of rigidity will change. So this time the G is equal to 2116.24 Newton per millimeter square. To calculate the average of modulus of rigidity of steel, we will take the two values that we get from 400 mm and 200 mm and divide by 2. So for the steel solid bar, the average of modulus of rigidity of steel is equals to 1425.775 per millimeter square. After the calculation, we will get the data for shear rigidity modulus G for each load. The average G for the steel solid bar is 1425.67. For aluminium solid bar is 1384.30. And the last is nylon solid bar, which is 89.285. The second question is the comparison between 3 different types of bar with different lengths of rotation pointer from the fixed cap. According to the data table in table 1, 2, and 3, when the length of rotation, scale, and pointer from the fixed cap is at 200 mm, steel solid bar has the least increment of angle of twist, followed by aluminium solid bar and nylon solid bar. Even though the weight of load is different from nylon solid bar, which is with an increment 1 Newton in a range of 1 Newton to 8 Newton to the others 2 bar, due to it cannot support the weight of the loads with increment of 5 Newton from 5 Newton to 40 Newton. When the length of rotation scale and pointer from the fixed cam is 40 mm, you can notice that when the weight of loads increases, the angle of twist on each steel bar, aluminium bar, and nylon bar also increases. The increment in angle of twist for aluminium solid bar with the same increment in load supply is larger than steel bar. However, the nylon solid bar has the most obvious increment in the angle of twist among 3 solid bars, even with a smaller increment in width of slots. The third question is, based on your findings, explain the relationship between the modulus of rigidity of material with the parameters such as types of materials for the bar, length of the bar, the shape of the bar, and polar moment of inertia. Based on the result of this experiment, the modulus of rigidity of material depends on the type of material. The higher of the modulus of rigidity of material G, the more rigid and resistant of the bar towards the shear deformation. The relationship between G, bar length L, and polar moment of inertia J was expressed through the equation below. A high modulus of rigidity indicates that the material will hold its shape and that a substantial force will be required to distort it. In contrast, a low shear modulus means that the material is soft or flexible. Fluids have the lowest stiffness modulus and they begin to flow after shear tension applied in a minimum amount.
From this experiment, we can conclude that the objective of the experiment has been achieved, as the relationship between torque and the angle of twist of a circular cross-section specimen or material and the length of the shaft is obtained. It is proved that the torque is directly proportional to the angle of twist, and the angle of twist is also proportional to the length of the shaft, as shown in the formula below, which is angle of twist is equal to the torque exerted on the shaft times the length of the shaft over the modulus of rigidity times the polar moment of inertia. From the experiment, the modulus of rigidity G obtained for steel is 1425.775 Newton per millimeter square, aluminium is 1384.3 Newton per millimeter square, and nylon is 89.285 Newton per millimeter square. So from the value we obtained in this experiment, the value of modulus of rigidity G of the steel is higher than aluminium and nylon. The value of G is higher when the material is rigid and more resistant toward the shear of deformation. The low value of G indicates that the material is soft or flexible with only a little of force required to cause the deformation.
Safety procedure. First, we must inspect our equipment. Before starting the experiment, we must inspect all the equipment, including the torsion apparatus, clamps, bar, and measuring instrument to ensure they are in a good condition. Secondly, we must wear the personal protective equipment (PPE), such as safety goggles, gloves, and closed-stitch shoes to protect against potential injuries. Next, we must tie back our long hair and avoid wearing loose clothes that could get caught in equipment. And third, we must clear our work area of any accessory item or obstruction to prevent tripping hazard. And lastly, we have proper handling of equipment. We must handle off the equipment with care and follow the manufacturer instruction for setup and operation. This is the reference that we use for this experiment. Thank you.